So we've discussed K-colorability, what it means for a graph to be K-colorable. I want to focus now on two colorable graphs. So this means that the vertices can be assigned one of two possible colors in such a way that I never get an edge between two vertices of the same color. Okay? These graphs are called bipartite graphs, and they show up in lots of different contexts. Whenever we're assigning and pairing things off, like if we're maybe assigning computers to printers or applicants to jobs, that's an example of when we have a bipartite graph structure. So these come up often and they're worth a little extra thought. Now, we saw that a tree is an example of a bipartite graph, but also you can have cycles. For example, if I put this edge in here, I've created a cycle, but I still have a bipartite graph. And similarly, down here, I still have a bipartite graph. But what I cannot do is put an edge here. Why not? Well, it's a monochromatic edge, but we can look and see this is a cycle that's odd length. And that's why we saw before that it's 3 colorable, but not 2 colorable if I have an odd length cycle. So let's remember that if we have C2N is bipartite. So if we have an even length cycle, we do get a bipartite graph. And if we have an odd length cycle, it's not bipartite. The chromatic number of C2N minus 1, the minimum number of colors needed to properly color the graph, is 3. So let's think, how can we characterize bipartite graphs? That's what we want to do first. We saw that trees work, trees have no cycles, even cycles work, odd cycles don't work. So what can we say in general? The theorem is that G is bipartite if and only if it has no odd length cycle. So that's kind of a nice statement. Whenever we have an if and only if, we know that that's pretty much as good as we can get. It's a complete characterization. So let's see why this is true. There are 2 things to prove, right? An if and only if statement always has 2 halves. So since we know that the chromatic number of C2N minus 1 is equal to 3, if G has an odd cycle, then we know that chi of G is greater than or equal to 3. If you need 3 colors for a cycle, and you've got a cycle, you need at least 3 colors. So that proves that G is bipartite only if it has no odd cycle. So what we need to do is prove the other direction. The other direction is, let's assume that G has no odd cycle. And let's prove that we can 2-color it. And let's do it constructively. Let's just take our graph and color it. And let's do it in the same way that we've done it here. So what I want to do is I want to choose any vertex at all. So any vertex in the vertex set of my graph, okay? And we want to color V purple, okay? And now what I'm going to do is I'm going to tell you a rule for coloring every other vertex. So we're going to color W one of 2 possible options. We're going to color it purple if the distance from V to W is even. Otherwise, we'll color it orange. So this is if the distance from V to W is odd. So let's check that we've done that correctly in this graph, where we're going to have to substitute, I guess, okay, we can at least be half right. Okay, so we start here with green, right? And we say, okay, well, how do I know this one's green? Well, because the distance here is 2. Now, what's the distance in a graph? So I could get from here to here, right? I could do it by going all the way around here. But the distance in the graph is the shortest possible path, the length of any shortest possible path, okay? So that makes this coloring scheme well-defined. What's not clear is that when I color it in this way, I'm not going to end up with a monochromatic edge. So let's think about why that is the case. So let's take our initial vertex. Maybe we'll make it nice and big so we can see this is our initial guy, okay? That's our first vertex, V. Now, how do I know that I don't come down here later and I've got some guy that's like some number of edges away and some number of edges away. I've got 2 green ones and they have an edge between them. Okay, how do I know that that doesn't happen? Well, if we think about it, How do I know this doesn't happen? Well, here, this is going to have to be an even length path. And here, this is going to have to be an even length path. So we got even plus even, that's an even number, plus 1. That's an odd number. This would constitute an odd cycle, which we don't have in our graph. But what if they get colored the other colors? Now, can the same argument work? This path is now an odd number. This path is now an odd number. Odd plus odd is even. Plus 1 more makes it odd. So once again, we have an odd cycle. So since we don't ever have an odd cycle in G, we know that we can do this. We know that we can get this coloring scheme to work and never give us a monochromatic edge. So we now have a complete characterization of bipartite graphs. They are exactly those graphs that have no odd length cycles.